In this video, we're going to talk about plastic strains, and also we're going to see an explanation of why and how failure happens in geomaterials. In chapter 3, we mostly talked about elastic strains and strains which are recoverable. We touched a little bit on elastoplasticity and viscoelasticity, but most of that was about elastic strains. And in chapter 4, we explored what is the limit for those elastic strains. For example, we saw that we have limits for tension, for shear, and for compression stresses. These are the limits at which we don't have elastic strains anymore. But what happens when you get to that limit? How can you quantify deformation beyond those limits? That's what we're going to see right now. So let's go to this topic. And here, what we're going to do is we're going to see briefly how we can plastify or how we can quantify strains beyond the elastic point. These plastic strains which are permanent. All right, in order to help the discussion for this video and for this topic, let's see a video. Here we can see an example of a cylinder of brass loaded, and let's continue with the video. You see that the load will start increasing. Let's stop it over there. We already have about 10 tons, metric tons applied on this piece of brass, and we don't see any visible deformation with our eyes, but for sure if we were to measure deformation, we will measure the deformation that will be inversely proportional to the Young modulus of the rock, or in this case of this piece of brass. So let's continue loading. There's going to be a limit. Okay, let me stop. I don't know if you saw that, but how probably now you can see also with your eyes how this is deforming, and it's beyond the limit of which this material can take. And so now it's taking plastic deformation. And now you're going to see it's very evident that it is deforming, and at some point that is going to that was a video, and now it's pretty evident that we have deformed this piece of brass. Let me run it again to a state in which those strains are going to be permanent. It's not going to be possible to recover those. All right, so let's see. And now what it follows is an unloading, and you see that with the unloading, the shape remains like that. All right, this material is what is called a ductile material because it didn't fracture as it was loaded and as it was deformed. So let's come back here to our previous plot. Here you have a schematic of what would happen in this case and this type of loading, in which we first are in the elastic regime. After we go to the maximum, we go into the plastic regime, and even if we unload the sample, there is going to be a permanent deformation. Our objective is going to be to understand and also to quantify what are these plastic strains and why. Why do we want to do this? Well, what we have learned so far about elasticity is just very restricted to this range in which we have elastic strains. Actually, in nature and in engineering applications, many times we go into this regime, which is a plastic regime. So let me show here a few examples about that. Here we have a wellbore that has failed in shear, and you can see that around the wellbore there are many shear fractures in which the rock is experiencing a plastic deformation. Let's see another example over here. This is how we're going to explain the displacement of faults. How did, for example, this piece of rock moved relative to that one. We cannot explain that with just simple elasticity. This is an irrecoverable deformation, and it's a displacement from this region respect to this region that has to be explained through this plasticity theory. And one more example, how do we get from flat and continuous layers to layers which are deformed, like for example in this anticline, and that are fractured? Also, in order to predict this, we're going to need the theory of plasticity. Well, what we have learned about elasticity was actually quite a bit, and good news for you is that we are not that behind in the understanding and the quantification of plastic strains, and we're not going to see this in detail, but recent advances in structural geology, thanks to the theory of plasticity, now can help us predict similar shapes of these layers, which are folded and folded that we couldn't do before, but now thanks to this theory and the computational power that we have today, we can recreate these in computer models. Okay, let's come back over here. In order to predict these plastic strains, what I'm going to have, or what I'm going to need, is a plasticity theory that is going to allow me to predict these plastic strains to what is called a plastic stiffness matrix. Similarly to what we saw for elasticity, and we had an elastic stiffness matrix that related stresses to strains, with plasticity we're going to have something similar. But now we're going to have a stiffness plasticity matrix, and that matrix is going to depend on the model that we choose, and in general there are going to be several options for that. Something very interesting about this type of failure and permanent deformation beyond the elastic point is that these deformations are going to depend on a few variables, and principally is going to depend on the effective mean stress, which in most uh, geological settings is going to depend on depth. And what we see with these kind of materials and with rocks is that depending what is the effective mean stress or the confining pressure, or in terms of a geological setting, the deeper you go in from the surface, the material could behave as a brittle material or as a ductile material. So what is this? Uh, Let me show here an image in order to uh, better understand what's going on. Here you see examples of rocks, and I believe this is a marble which was failed at different confining pressures. For example, this one, it's the rock without any stress applied. This one is the one that is failed under unconfined conditions, and we can see a clear fracture that goes through the rock. If we keep on increasing the confining pressure, which would be equivalent to getting this rock into deeper and deeper locations, we see that the mode of failure starts to change. And as I go deeper and deeper, I go from just one single fracture localized just in one region to multiple fractures that are much smaller than this one and that are distributed along the sample. And this type of failure, with failure just concentrated in just a single plane, is what is called a brittle failure. And a distributed failure, which it's not just one, but there are many next to each other, results in ductile failure, in which we don't see any clear fracture that happens along the material. And for example, in this case, like in these three cases, the material will not shatter when if this fail, it will just keep its shape opposite to this one that probably when it breaks, it's just going to break into pieces. So this type of failure is brittle, this type of failure is ductile. And when we actually measure those stresses, we see something very similar to what we see over here, in which if we have no confinement, this is the maximum stress that we can apply, the deviatoric stress in this case. And if we keep on increasing the confining, we go into this ductile regime in which we have significant plastic strains, and the strength of the material is actually higher. The higher the confining pressure, or the higher the effective stress, the higher the strength of the material is going to be, and also the more ductile response I'm going to have. Notice that in this particular case, at a very high stress, we never reach a peak stress. The material always gets stronger and stronger. And this is what we have seen, for example, with the Moore Coulomb shear failure theory, that the higher the confining, the bigger the Moore circle I'm going to have, and the bigger the strength of the material is going to be. This just reminds me something, and let me bring this into here so I can explain myself a little bit better. So the Moore Coulomb failure material or criterion is this one, in which the higher the confining, the higher the diameter of the circle, and this brings a lesson to me, which is that materials have a property that the more stress you put on them, the stronger they get. And this is given by this failure criterion. And also you should be like rocks. The more stress you have, the stronger you get. And this is what we see in this data over here. The higher the confining pressure, or the higher the stress, the stronger the rock gets. Okay, so we have seen that we can have brittle failure and we can have ductile failure in rocks, and that depends on the effective mean stress, and in terms of the geological setting, that also depends on the depth. The deeper you go, the more likely is that you're going to have ductile failure. The closer to the surface you are, the more likely it's going to be that you're going to have brittle failure. And the transition going from brittle to ductile, as we said, it depends on the mean stress, and here we have a schematic about this. A brittle material is going to fail right away. A material that when it goes into the maximum stress, it goes more or less with the same, it can hold the same strength and it doesn't vary much, like for example this case, is what we call a perfect plastic material. A material that after reaching the peak decreases in strength is what we call a strain softening material, because as you increase the strain, the material gets softer, or you could say also weaker. And this is what we call a strain hardening material, because as you go over the yield stress value, the material gets stiffer, well, not actually stiffer, but it gets stronger and stronger. This is a material which is strain hardening. And in order to calculate those plastic strains, then you will need a model for that, and you will need this additional plastic strain stiffness matrix. Okay, coming back to practice and to the physics of failure of rocks, this transition from brittle to ductile is going to depend on several variables. One of those, and the one that we see over here, is confining stress. Also, temperature can result in this variation from brittle to ductile. You can imagine that as we increase the temperature, many rocks are going to start to get more ductile. So the higher the temperature, the more ductile rocks are going to become. And the same thing applies to the reasoning we were doing with the analysis with depth. The deeper you go, the hotter it gets into the subsurface, and also the more likely it's going to be that rocks are going to fail ductilely at a great depth than opposed to the crust, where the deformation and the failure is going to be more brittle. And another parameter that's going to affect that, it's also the loading rate. Usually, the slower you fail a rock, the more chances you are going to have to develop a ductile behavior. Mineralogy is also important. For example, there are some sediments, like for example the non-cemented sand, which is it develops mostly ductile deformation or ductile failure beyond the yield stress, but also rocks can develop ductile deformation, particularly for shales. The higher the organic content and the clay content, the more ductile a shale is going to be. There are some shales which are brittle, and it happens in some of those that the higher the carbonate content, the more brittle the rock is going to be. And in terms of hydraulic fracturing, that's something that can be quite important, because usually for hydraulic fracturing it's preferred to have a brittle failure so that fractures create more branched fractures, opposite to what you would have in a ductile formation or in a formation that experiences ductile failure. In a formation which is more ductile, you would just expect a single fracture, and it would be wider and shorter than what you would have in a brittle formation. And last, specimen size is also important. Usually, the bigger we go into taking a specimen of rock, the more likely it's going to be that we find heterogeneities and discontinuities, and those heterogeneities and discontinuities are going to favor a more ductile formation at a larger scale than at a small scale. At a small scale, in a simple piece of rock which doesn't have any fractures, which doesn't have any discontinuities, you should expect, if the rock is brittle, a brittle failure. But that same brittle rock, if you put it into a larger specimen with fractures, with discontinuities, when you load it, it's more likely that it's going to develop a ductile deformation, because the fractures are going to slide with respect to each other. All right, so let me see if I forget something from here, and I don't think so. So remember that this transition from brittle to ductile failure is very important, and it helps us to understand modes of deformation that are not just elastic but are also plastic, and that happen in nature and also in applications, like for example in wellbore failure. All right, now that we have all this knowledge about how rocks fail and what happens beyond the elastic point, let's go to the next topic, which is taking a look again about why rocks fail and how rocks fail. And let's see two quite different kind of materials. For example, here we have an example of an uncemented sand. And an uncemented sand is going to have a mode of failure which is significantly different from that of the rock. For example, if we were to load a sand under a triaxial state of stress in which we increase the axial stress and we keep the confining pressure constant, what we will see is a failure in shear. And this shearing is going to localize, as we see in this example, and the failure is going to happen not through a single fracture, but through rotation and sliding of the grains with respect to each other. And this is the case, for example, let me come back over here and go to the first topic that we saw. And this is the example of the sand dunes, in which when this material fails, it fails by displacement of the grains and sliding of the grains and rotation of the grains at the zone of failure. And that's exactly what we see over here, where in this example we see how, and this is a real test, uh, how grains rotate at the zone of failure. So we see that we don't have a single fracture, but it's more a distributed failure. And this is what happens in, for example, in uncemented sand. In cemented rock, it's going to be different. And in a cemented rock, we can also have failure that happens through fractures, which are localized and which are going to depend on the type of stress that it's been applied. And there are three types of fractures that can occur in these cemented materials. And these go by the names of mode 1, mode 2, and mode 3. In the mode 1 type of fracture, what we see is an opening of the two faces with respect to each other. And this is usually caused by tensile failure, and it's called opening modes, again because the two parts of the faces of the fracture open with respect to each other. This is what is going to occur, for example, when we do a hydraulic fracture and we have a fluid-driven fracture where the fluid is going to pressurize the fracture and split the two parts and make an opening with respect to each other. The two other modes are related to shear, and we have something which is called the in-plane shear mode and the out-of-plane shear mode. In the in-plane shear mode, as you can see in the figure, we have a shear which applies a displacement which is in the same direction of the propagation of the fracture. So here's the tip. If I were to propagate this fracture would go and continue in this direction. And then we have the out-of-plane shear fracture, in which we have also shearing, but notice that the direction of the stresses it's in another direction compared to the direction of the fracture itself. And these three processes are going to contribute to the failure of rocks. When we load a rock in nature, in the field, or in the laboratory, actually what happens is that many times we are, for example, stressing the tips of pre-existing fractures that later, as they join with other small fractures, they create a big fracture, and that's what we eventually see at the larger scale. This is what we see in this example over here, where loading of a rock results in creation of small fractures that, as those fractures start to coalesce with respect with each other, they form a large shear fracture that is what we eventually see. And that's what eventually forms a shear fracture in a cemented rock. Okay, so these two types of failures then are very important in order to understand how rocks and sediments fail. And depending on what kind of material I have, then that's going to give me the choice of what kind of constitutive model or plastic model I choose in order to predict the strains beyond the elastic limits. And this is not something that we're going to do in this class, but this is something that you should be aware of, that there are going to be different type of models that are going to apply to different kind of materials. And before you choose those models, then you need to know what kind of material you are dealing with.